All right, so what's happening now? So you can see your programming test 1 result. I will definitely try to release it by the coming Friday. I know it's a drop deadline, but hopefully everybody will stay, but I'll still give you the feedback and the result. Hopefully by the end of Thursday, but Friday, maybe the latest. The TAs are very busy grading them, and then once I get the result, I need to do a quick check, and then I should be able to release them. But by the end of Thursday, hopefully. And for your lab number 3, which will be the basis for your programming test number 2, that one there will be released by the end of this coming Thursday, so you can definitely take a look. That one is going to be pretty much self-guided about how you can interact with the prover in Rodent. So you will just have to make sure you follow step by step and also understand the logic over there. And the TAs will be there, and I'll be in my office hour. You can definitely drop by and just practice to get for your final assessment programming test 2. And don't forget, we also got the makeup lectures for you. I already released them last week this time. Let me remind you once more. Okay, if you actually go to the 2342 lecture site, you will see all the way at the bottom there on the table, right? So these are the makeup lecture for all the test time that we actually missed. Okay, it's a new study there, which will talk about initial model and also the first refinements. And you will definitely gain some benefits from there by studying that, right? All right, guys, any questions so far? You good? Alrighty, let's now continue. All right, let's see what we did last time. I'll switch to iPad in just one moment. I think it may not be a bad idea to have a very quick recap about what we covered last time. So last time we introduced this very first refinements for the bridge controller, okay? And we talk about moving from this initial abstraction where there's no distinction between the bridge and the island. And now we do have a notion about bridge. And more than that, it's actually one way. So we have to make sure we use the quantities A, B, and C to restrict the way bridge is going to work. And we'll do a little bit more today. And we talk about over here about the various invariants over here in the new model, and we also derived them together last time. Okay, invariant 4 and invariant number 5. You want to make sure you also know how to derive similar invariants, maybe in the future assessment. And we talk about ML out and ML in. So these are the events that actually exist in both the initial model and the first refinements. That means their guards and also their action should somehow be, let me say, overridden, in Java term, which means they have to somehow be redefined in a way that's consistent. So I showed to you guys last time about how you figure out the 2 guards over here and the 1 single guard over here, right? You want to review the lecture and see how we derive them. And also we talk about the actions, which is pretty much consistent. One thing which I maybe briefly mentioned, but I didn't really say in detail, which I'm going to do today. You really want to think about if I'm talking about this ML out event here, which exists in both the first refinements and in the initial model. How is this going to work consistently in the 2 levels of abstraction? That's something I will try to visualize for you today. And also we need to also look at some proof obligation. We'll look at some of them, but we'll look at the other half, maybe on Thursday. Okay? And then we talk about the comparison between ML out, abstract version, ML out, concrete version, and also ML in, abstract version, ML in, concrete version in the 2 models, right? Okay, just make sure you actually review them. And that's about it, what we covered last time. Do you guys have any questions? We're good? Okay, one thing I just forgot, okay, which is also very important. You may also want to take a look at the semester calendar to see where we are. Okay, let's now take a look at again together. All right, so we are now over here, right? We are now on lecture 17 on the 14th of March. And then your written test number 2 is going to happen next Thursday. Not the coming one, but next Thursday. I will make sure I release some study guide and also some practice question to you like last time. Hopefully before your Thursday's class. And you will definitely wouldn't hurt to actually start preparing for your written test number 2. It's not going to be cumulative, which means whatever we have covered already in the written test 1 is not going to cover again in written test 2. But we'll cover everything in the final exam, right? So you may want to take a look for just to get prepared for written test 2. All right, that's something I kind of forgot to mention.
The final exam is going to have like, is the final exam going to involve actual programming or actual?
Nope, the final exam is going to be paper test, but it doesn't really mean I cannot ask you questions related to rodent. It's also possible, but it's going to be a paper exam.
Okay. Well.
Okay.
At least they're not going to be.
Alrighty. All right, let's now move on to talk about more interesting stuff about this refinement here. So we'll learn about many interesting concepts that only exist when you talk about refinements. Okay. Let's see a little bit slides here. So we talk about before and after predicates. So the only thing I want to remind you guys is here. Okay, let me just switch to iPad over here. Okay, if you look at the events over here. So if you look at it, ML in and ML out, right? So these two are the concrete version of the events because they got the abstract version in the initial model. Concrete events. And you may want to understand this one here as the concrete guards because we will have to say something about the guards. We're going to prove something about it today. Very soon, maybe after the little break. So these are called the concrete guards. And similarly, over here would be concrete actions. We wouldn't talk too much about concrete actions today, about how they may preserve the invariance. Then most likely we're going to do that on Thursday. But for today, we're going to focus more on the guards of the events. Okay. And then, what about the before-after predicates? Whenever you want to do any formulation of the sequence to represent proof obligation, you always have to do the substitution as indicated by the before-after predicates. Okay. So just for example, which I mentioned last time, may not hurt to emphasize again. If you look at this particular action, it only talks about A should become, in the post states, this particular evaluation, which is A plus 1. However, we didn't really mention about what's going to happen to B and C. So they simply mean they don't really change. Okay? That's something you will have to remember. So B and C, absent from over here. That means they stay unchanged. So you can see very obviously here, A prime equals A plus 1 is corresponding to this. On the other hand, B and C, they simply stay the same in their post states. Okay, so you need action. So to be the 100% precise, you want to really think about what the before-after predicate is, rather than just the action. The action itself sometimes may be a little bit implicit about what may not change. All right? All right, so that's the first part about before-after predicate. We'll need this very badly when we formulate a sequence very soon. Okay, the next one, we want to go a little bit about how we can make transitions. So this is the place I would like to give you guys some very visual idea about how the abstract transition and the concrete transition are going to happen simultaneously in your mind. Okay, that's something we'll do. Let me see if there's anything to say on the slides, and I'll switch back to draw you some diagram. Okay, we got abstract state, concrete state. Oh, by the way, so this slide here has also been talked about last time. Okay, so I don't need to repeat. Okay, events. So let's talk about how we can make a transition to modify variable. And now we've got two sets of variable, either on the abstract version or the concrete version. We're going to see how they may correspond to each other. All right, so you want to think about we got two abstract events in the initial model. We got ML out, ML in. You can see they only try to modify n over here. Oh, beg your pardon, this is apparently a typo. I'll fix that. It should be n becomes n plus 1. The a becomes there is apparently wrong. Okay, I'll fix that. Okay. And then you can see the corresponding concrete version over there. That one there, as we just went over, is going to modify the concrete states over here. Let's see visually how things should work. And then from there, I can hand wave a little bit about the two kinds of proof obligation we have to prove about refinements. Okay, let's do that exercise together. All right. Let's now take a look. And let's understand what's really on this page over here. This part here is the abstract model, right? We got N here, the abstract states. We got some invariants here, and also abstract guard. We got abstract action, okay? So here, this part here is the concrete model, the first refinements. We have the refined states or concrete states, and we got 5 invariant here, which we talked about last time. And then we got the concrete version of the events, concrete guards, and also concrete action. All right? And let's now try to visualize what's going to happen. Let me consider a very simple trace. So I'll put it on the top over here. So let's say we want to consider an execution, a particular execution, just as an example. Init, followed by ML out, followed by ML in. Okay, that's a very short trace we would like to do. I'm only going to do until over here, and hopefully you will get a very concrete idea what's going on. And then a little exercise will be for you to finish the last events at both the abstract and concrete states. Let's see how that goes. Okay? And to really draw the states for abstract version, we only got the constant D, right? The number of cars maximum. And also we got some variable N, right? That's something we got to fill out. And also we got the concrete states, which we still have D over there. But now A, B, and C will be the concrete variables that we have to worry about. Right? So that's why the state is going to be represented by A, B, and C. All right, let's see what's going to happen. Let me start with the concrete, because we are now dealing with refinements. So what I will do is, let me make a copy of this. And then I'm going to, let me do it again. It's good to include a circle, of course. Okay, let's say over here. And for the concrete version, of course, we're going to have some init. Okay? And we haven't really spoken about the init event just yet, but it's going to be very straightforward. In this case, no cars should be in the island or on the bridge. So that means A, B, and C should be just 0. No traffic flow and no cars in the island. Okay? So we're going to put just 0, 0, and 0. Okay? Now, how is this simple initialization for the concrete states going to correspond to the abstract states, which can also initialize another version of the system, right? So now we talk about initializing different version of the system, abstract version versus concrete version. If you think about it, we are going to also make a diagram of this. Okay? So let me just make a copy over here. Okay? I'll also make it a little bit smaller, just over here. Okay, for this abstract version here, we're going to have init events. And notice that this is the init in the initial model, which we spoke about is simply going to initialize n to be 0. This is the init that's going to happen in the refinement model. And I'm telling you ahead, we're just going to assign A, B, and C to be 0. Okay? So that means n is going to be 0. All right? So far, I have done 2 things. Number 1, I have initialized a concrete state. I have also initialized an abstract state. But we shouldn't really think of them in isolation. They are related somehow. And do you guys see which constraint we have specified so far? Link them together. Invariant 4. Okay, excuse me. Okay, that's very nice. And that's exactly right. Because we said before, this invariant here involves both the abstract variable and the concrete variable, for sure. That's the one. All right? So one thing, later on, if you ever have to use this approach again, let's say beyond this course, when you're building your refinement model, always remember there should be at least one invariance that should involve both the abstract and concrete variable to relate them together. So this is how you can draw connection between the two. Okay, so let's now try to link them together. Between these two states, I know that invariance 1, 4. Invariance 1, 4 is satisfied because A plus B plus C equals 0, 0, 0, which is equal to n, which is also 0. All right? So this is a little bit something a little bit more visual to show to you these two states are indeed related. Think about what you're trying to do, simultaneous run of these two state machines. One is abstract, the other one is concrete, but they are really related to each other. They are somehow connected in a formal way. That's about the initial events. Let's do one more event. Remember the trace we wanted to follow through? We have done just init. Let's do ML out, just to emphasize the idea even more. Okay? Again, I'm going to start with the concrete states. Let's say I try to do, over here, another transition. That one there is going to be ML out. And that one there is going to give me a new state. Let me just copy that, and then you can easily see that too. Okay, let me just wipe out what's not right over here. All right, so now how can we figure out going from here to here by an occurrence of ML out? And notice that the ML out over here is a concrete ML out, right? Which is over here. So what should we do? Well, there is going to increment A by 1. Agree? There. Going to be 1, 0, 0, right? So it's going to be 1, 0, and 0. So notice that this is the main change. One more thing to say that's kind of implicit. Why are we able to actually take an occurrence of ML out? It is because ML out's guard is actually satisfied, right? You can see from this state over here, A plus B, 0 plus 0 is going to be 0. 0 is less than D, which is 2, that we assume. And then C is also equal to 0, right? That's something implicit you want to know too. You can only take an event for action if its guard is enabled. All right, so this is a concrete version, right? Let me just, concrete version. All right, let's now do the abstract version, and then we'll see how they are related, and then I'll give you the little exercise to do. So what we want to do now is to take also ML out, and now notice that it's also called ML out, but that's the abstract version. ML out, let me put it here, okay, ML out, and this one here is the abstract version. Okay, let's now put the state here, over here, okay? And according to the action, it's going to increment n just by 1, all right? It's going to go from 0 to 1. And what should we do now? What we should do is we want to make sure these two states, by taking the same events, one is abstract version, the other one is concrete version, these two states will still be related by the gluing invariance, the linking invariance. Okay? So what we'll do is we're going to try to link them again by the same invariance, which is invariant 1, 4. So invariance 1, 4, okay, let's try A plus B plus C. A plus B plus C, which is plus 1, so that'll be 1, which is equal to n, which is also 1. Right? Of course, the actual run for the system can be much more complicated, but I'm just showing you the simple step. At least you know how to link the states together. And exercise for you, and then I'll recap. So let me get this away, and also move this away. What you really want to do is to really see if you try to do further transition for MLN, what's going to happen? You might have MLN over here. You also have MLN over here. And then once you get to certain states over here, you get to certain state over here, how are these two states related? That's something I would like you to complete the diagram. Should be rather easy, but I think it's good to do it. Okay, let me recap. The very important message from here is, when you think about refinement model, especially you think about every model like an abstract state machine, right? Like a state machine. The state machine for the refinement model and the state machine for the abstract model, they don't really just work without any connection. Indeed, they do. The way they actually get related is by the corresponding invariants that involve the concrete variables and the abstract variable. You want to always remember, whenever you make a transition at the concrete level, there's always some corresponding transition in the abstract model. Okay? That's something we have to put more formally. Okay? Are we good so far? Okay, let me now say two more things, and then we will be ready to get things a little bit more formal. What you want to really look at would be, for this ML out, which is abstract, and also for this ML out, which is concrete. Okay? There are two things we have to do to prove about the refinements. Number one is the abstract guard versus the concrete guard. How should they be related? More i.e., this guard here and this guard over here, right? You can see the abstract guard and the concrete guard. How should they be related? That would be one example. This one here and this one here. How should they be related? I'll put a question mark. And number two, the abstract action versus concrete action. Meaning that, so this is the abstract action. This part over here, let me use a different color. So this is the abstract action over here. This is the concrete action. How are they related to each other? That's another issue to be addressed. I will try to address about the guards today. And then I'll talk about the action, which has something to do with invariant preservation on Thursday. But today we'll do the guard, so-called guard strengthening rule. We'll talk about it, we'll formulate it, and we'll try to do proof together. Okay? All right, guys, before I move on, any questions? You want me to clarify anything? Okay. Yeah, so far it's still not too heavy, I hope. Okay. And the good news today, we don't really have any new inference rule to show. Okay, so that's good. So all the inference rules you have learned so far are good enough to do any proof. All right, before we actually can formulate things, we have to mention the components that we will need. So if you look at the slides over here. Yeah, the components, we just got different stuff. Okay, let's take a look. I'll just show it to you. Because when you see the proof obligation rule, you'll see these formal components. You just need to make sure what they really correspond to in the model. Again, we got abstract model here. We got concrete model over here, or refinement model. Number one is something we learned before about the pre and post states for the variable, right? So v and also v prime. So this one here, right? You can think about this is the v. Of course, v prime over here is simply correspond to n prime. And we also have w and w prime, right? These are the concrete variables in the pre and post states. So you can think about these are the variables. And if you only talk about w, it's going to be a, b, and c. W prime in the post states, just prime them. A prime, b prime, and c prime. Very straightforward. Okay? And then for the invariants, that's what we learned before. Before we only had one model. So there's no notion about abstract versus concrete. But now we do. The abstract invariants, right? Abstract invariants over here has these two. These are the abstract invariants. And here are the concrete invariants. So here are the concrete invariants. The only thing I want you to pay a little bit more attention to is about the variables that might get involved. You can see here, for the abstract invariants, we only involve the abstract variable v, right? And then for the concrete invariant, j, it involves both the v over here and also the w in the concrete states, okay? It's a bit abstract, I know, but that's the formal rule. Finally, let's now take a look at the guard. Okay? The guard in the abstract states will be called G. Okay? So you can think about just one example here. You can say the guard, and then we got constant D, right? The same constant. And also we got the variable N. Let's talk about MLL only. For MLN, you can just make the similar derivation. ML out. Right? It's going to be the abstract guard for ML out. That one there would just be N less than D. Okay, just this one. On the other hand, there is another new alphabet called H. That will be the concrete guard for the corresponding event that's refined. Okay? And we know ML out, the concrete version is over here. All right? So this will be the concrete guards. So the formal way to put it would be, you would say the H, the concrete guard, which will involve the constant, which is still D, they share, and also a concrete variable, which will be A, B, and C, right? A, B, and C, the concrete variable. In this case, it will be the guards over here. It will be A plus B less than D, and C equals 0, right? Just two guards, okay? I wouldn't really say, okay, I tell you what I might ask you in the test, what I wouldn't ask you in the test. That's also very relevant, right? Okay. I wouldn't say, okay, now given these two, tell me what G is, what H is. That's a little bit too dry. So the reason I'm going over with you about these formal components is because when you look at the proof obligation rule, they use these components to specify the rule. So that's why you should really know where to extract from the model. That's why I'm showing to you. But I wouldn't really say, give me this from the model, right? That might be a simple question, but it's, to me, there's no point. Okay, finally, about the effects. Okay, for the effects over here, again, we got abstract effects and concrete effects. Okay, let me give you one example right away. Okay, think about this is the abstract effects for ML out. Abstract effects or abstract action. And this one here is a concrete effects. Okay? And when you think about the effects formally, think about before after predicates. Okay? Let me write down two examples. You can think about the abstract effects. And again, we got the D as a constant, and then we got N as an abstract variable. Right? And when we talk about ML out, it's going to be a list of values the post state is going to take, right? N is going to take N plus 1. So that's why you put N plus 1 over here. And there's only one variable, so nothing else. Okay? But F will be a little bit trickier. It's a concrete effects. What about the C? The same. That'll be just D. B, A, B, and C. A, B, and C of ML out. Okay, so it's still going to be a sequence, all right? But now this sequence here, the length should really correspond to how many concrete variables you have. You actually have 3 variables. So there should be 3 spots that you want to fill out. Right, the first spot should be, what should be the post state value for A? That one's easy. It's going to become A plus 1. What about the post state value for B? Just B, right? Because it's implicit, right? That's the part you want to pay attention to, all right? B and C. So all these formal components are useful implicitly because when you figure out the proof obligation sequence, these are the things you will need to understand how to extract from the model. All right, guys, any questions until now? Are we good? All right, I think it's now a good time to take a short break and take attendance because after break, we can talk about the first refinement rule called guard strengthening. Okay, why don't we do that now and take a short break? Yeah, just get your device ready and then we'll take attendance. Poll. And then, all right, you guys can check in. Everybody's good about checking in? All right. And then I'm going to close it. All right, thank you so much. Let's take a 2-minute break, and then we'll come back about guard strengthening. All right, just one moment, and then we'll get started again. All right, guys, let's get started again. All right. All right, there's one more thing I'd like to mention, which I forgot before the break. Whenever you have the scenario where you got some concrete events, you got some abstract events, you're arguing that these events at the concrete level should really behave consistently with the event at the abstract level. There is some formal word for that, which I will also mention maybe next time. It's a little bit more sensible when you mention about it when you talk about invariant preservation. But for now, I'll just mention that. Okay? In general, think about this is some events that is concrete. And this is an event that's actually abstract. Okay, I'll write a little bit better. Think about this as an event that's actually abstract, ABS. Okay? So what we say is the events at the concrete level is simulated by the events at the abstract level. So direction is important. This event at the concrete level is simulated by the events at the abstract level. Okay, that's the terminology. But I'll get to it a little bit deeper next time. Okay. Okay, so let's now talk about guard strengthening. Okay, let's see anything else to mention in the slides. Before we sketch the proof obligation, let's now talk about something important. Okay, just clarify your understanding. And it has to do a little bit about when we talk about implication back in the math review. Okay, so now let's say we talk about the predicates or proposition. When we say P implies Q. Okay? And for our discussion about guard strengthening, you really want to understand in two ways. Okay? When we say P implies Q, one way to say it would be you can say P is stronger than Q. Yep, I'm not too sure. Maybe back in your 1019 or 1090, your professor mentioned about this term. If no, now be the time to learn it. Okay? It's actually very intuitive. I'll draw some diagram to also help you understand. symmetrically, you can also say Q is weaker than P. Okay, so these are the two textual terms you have to know. I'll give you an example, but let's now sketch that conceptually. The way to understand, I believe the best way, is to consider what are the sets of satisfying values. Okay, over here. If I say P implies Q, right? And then I'm saying that, let's say, for example, here, let's say P, this will be a set of satisfying value for P. Let me define that. Will just be all such X which satisfy P. Right? And also P of Y, Q. Q of X will just be all such X which satisfies Q. Okay, let me move this down a little bit. Let's say we're given these two definitions. We got Px and we got Qx. Px tells you all the set of all values that will make this predicate true. And Qx is the set of values that will make Q true. Now, if I tell you that P implies Q, can you picture the two sets together? Is one set larger than the other, or are they related in any way? So what you really want to consider is 1, 2, and 3. In that way, okay, you're saying that, I'll write it down. You're saying Q of X is a subset of P? Okay. Anybody else? Well, when you compare two sets, right? Basically, you got, this will definitely be one option. This will be another option. P of X equals Q of X. Number 3, let's say P of X subset of Q of X. These are 3 options. Of course, number 4 will be they are completely non-overlapping. Well, these are at least 4 options here we can consider. And what you said was this one here. Okay, I'll put a question mark for now. Okay, you changed your mind, right? I'm pretty sure. You want to go for number 3? Sure. I'll put a question mark here as well, right? Because they look pretty much similar, right? Why don't we use one simple very example to really illustrate this, okay? So why don't we say we have, let's say, P is P of X will just be X larger than 0. Okay, and then also we got Q of X, which is X larger than or equal to 0. Okay, first of all, do you guys agree? Based on this, I know that P of X implies Q of X. Yeah. Right, because if I know that something is positive, of course, it's not negative. But the other way is not right. Because what if this cannot imply this? Because what if it's equal to 0? In that case, it wouldn't imply. All right? Okay, let's understand that first. Okay, that one's for sure. Okay, so now how do we visualize it? Right? If we set about this guy here, right? Then, well, let's just draw the diagram. Let's say these are all the values where P of x will be satisfied, which means we're going to get 1, 2, 3, 4, and etc. Right? You can see this P here is the antecedents. Now, how do we visualize the satisfying value for the consequence? Should we draw something that's smaller by taking out some value? Or should we draw something that's bigger by including some other possibility? Yeah, now I'll let you correct yourself. Yes. Bigger, yes, exactly. Which value would that be? 0. Absolutely. All right. Okay, so over here, this will just be a bigger set over here. So this will be Q of x, and we just include 0 over here. All right. And so the correct answer from the previous question should be, this is right. Okay. And let me just draw that, and then I'll recap. Okay. Whenever you got two arbitrary predicates, P and Q, if you know that P implies Q is true, that would mean the satisfying value for P is going to be, like here, a subset of the satisfying value for Q, like over here, because you got P implies Q over here. Okay? Whenever you forgot, you can always just do something little example to remind yourself. And let me just draw one more time, abstractly, and then I'll clarify the term. And then we're done with this little digression. So think about here, we got P of x. Okay, so that will be the antecedents. And then for Q, we just got another one. Okay, that's the Q. Okay. Here, you can think about why do we say P is actually stronger. You want to think about the stronger the predicate is, the fewer values you will actually allow. Think about predicates more like a filtering function. The stronger it is, the more values you're going to filter out. So that's why less value will be satisfied. Right? This notion is actually very important. Later on, we'll talk about something called relative deadlock freedom. We also need this notion here. All right? Okay, so I'll just put down here, and then you guys can think about this concept over here a bit more. The stronger a predicate is, the more values it filters out. And of course, the less value you can really satisfy. All right? So we say that this is stronger. And this one here is weaker. Right? Just keep that in mind, the terminology. Whenever I say a predicate is stronger or a predicate is weaker, you should really know what I really meant by that. Okay? Okay, so we're now ready to talk about Gauss strengthening. Okay? And let me, before I ever even get to that page about formulating the sequence, let's now do one more. Okay? Let's say if I have, let's say, model 0. Okay? And then we got another model here that refines that. Model 1. Okay? Let's say we have some events over here. And the event, I'll just make it more explicit. Let's say abstract events. And also we got events that's concrete. Okay? And of course we have the notion about guards. Let's say when, and it's actually called G, right? And also we got another concrete guards when, that's called H. The proof obligation tells you that here is a principle. When a refinement is created, the guards of each event can only be strengthened. Or can only be stronger, either way. Right? This is actually very important to note. Okay, that's the rule. So how do we express that formally? In this case, it's going to be H, the concrete guard, should be no weaker than the abstract guard, right? It should be only strengthened. So that means H implies G. And I'll give you a little bit of intuition over here to see what that really means. When we say H implies G, that means the following. Whenever I'm able to make a concrete transition, that means this event is enabled. That implies logically, in the corresponding world, in the abstract model, I should also be able to make a transition for the counterpart for the abstract events. That should also be enabled. Okay, I'll write it down. Okay. There are two interpretations to this. I'll show you both. If a concrete transition. By the way, when I'm talking about concrete transition, I would like you to also go back, when you study for this, also go back to this diagram I talk about over here. If I'm able to make a concrete transition, that means a concrete transition is enabled. Logically it implies there should be also another counterpart scenario where the abstract events is also enabled. That's what we are talking about. Okay? All right, let's now go back here. If a concrete transition is enabled, which means H is true, then its abstract counterpart is also enabled. G, sorry. Okay, that's interpretation number one. If I'm able to make a transition at a refinement model, there's got to be a corresponding one in the abstract. I cannot create anything that does not exist in the abstract. Okay, number one. Number two, you guys remember contrapositive, right? Okay, when I say H implies G, you can think about another way, which is not G implies not H. Okay, for number two, it could be a little bit tricky. I'll just mention that anyway. If you can take it, take it. If not, forget about it. Okay, I'll just mention that. Okay, for number two, okay. This is really equivalent to not G implies not H. Now, how do we interpret this? This is something like this. If an event is not possible to occur in the abstract world, that means in the concrete counterparts, that particular occurrence is also not allowed. Meaning that in the concrete world, you're not allowed to create any new behavior. Okay? What's not allowed in the abstract transition is also not allowed for concrete transition. Okay, finally, final remark. In the concrete model, no new behavior is created. Yeah, there are many insights and details over here. Think about it. You know, when you can stay maybe isolated for yourself and then think about these issues. They're not too bad, and they just need some time to digest. All right, enough intuition. Let's now talk about how we can formulate the proof of obligation. If you look at the slides, I gave you, I believe, both about guard strengthening and also invariant preservation. Let's focus on just guard strengthening for today. All right, so that will be the intuition. Okay, and a concrete transition always has an abstract counterpart. That's good. Okay, do you guys remember only if? Okay, for this one, if you're not too sure about what only if really means, go back to your math lecture about implication. We got various ways of expressing about implication, okay? So what I'm saying over here in English, I simply mean the concrete guard should really implies the abstract guard, okay? That's basically what I just said on the page. Right, for invariant preservation, I'll suggest we ignore that just for today. We'll continue from there on Thursday, but let's now focus on guard strengthening. Okay, that's what we want to look at. And we might just be able to do some proofs. Okay, let's take a look. This will be the proof obligation you will have to formulate. Okay, let's now take a look. First and foremost, you have to know this guy here is the concrete guard. Concrete. That is why I had to show to you the formal component, G and H. Notice that the G here is actually indexed. So that means depending on how many abstract guard you might have, you may have to generate separate, different formula sequence. Okay. That's a concrete guard. And this part over here is the abstract guard. Okay. Okay, abstract guard, of course, let's say ML out, just for example. This will be the abstract guard. And this will be the concrete guard. And then we also have, this will be the axioms. And this will be the abstract invariance. And finally, we also have the concrete invariance. And of course, this is turnstile, right? In order to prove about guard strengthening, you have to put this much hypothesis. Of course, not necessarily every one of them will be useful. You have to use the monotonicity rule to drop some of them, but we'll see that. Okay? And then what we really want to prove is for every abstract guard, it should be implied by the corresponding hypothesis. Okay? Before I try to write down exactly what they should be like, but just remember this one here is the index of the abstract guard. Okay? So now here's a question for you guys right away. Given this proof obligation rule about guard strengthening, how many sequence in total should we generate? I'll give you a little bit hints, which is important. Because the only thing that's indexed, which might give you multiple possibility, is the abstract guard. So you basically have to count for how many abstract guard there are. Okay, 2, right? Yeah. 1 here and 1 here. Okay, 2. Okay, you basically just count how many abstract guards there are. Okay, the question answer to this will be 2. Okay, just the number of abstract guards. All right, you'll also see the similar reasoning on this slide as well. Okay, let's now try to put them together, and then we'll see how things will work. Let's say we now want to look at this abstract guard. Let's say that's what we want, right? So it's going to be a very giant sequence, and the consequence over there is going to be the abstract guard, which will be n less than d. Okay? I'll put it here, like that. What about this part over here, which is going to be the hypotheses? Okay, let's be very complete. Okay, what should I put there? First of all, we have axiom. So the axiom will be, I don't really have it over here, but you can look up in the previous model. I'll write it down. The axiom was D is a natural number. Okay, and also D larger than 0. Okay, if you look back to your initial model, right? Remember the axioms are shared. So they are axiom 0, 1. Axiom 0, 2. Right? So that's the axiom. And then we have the abstract invariance, which will be these two. Okay? N is a natural number, and also n less than or equal to d. So this will be invariance 0, 1, invariance 0, 2. And of course, when you try to put the formulation together, you don't need to include this part. I'm including it so it's easier for you to see the correspondence for the first time. And then we got concrete invariance. And how many? Yeah, I'll take a question a little bit later. How many concrete invariants do we have, guys? 5, exactly 5. Yes, I'll put it down. Yes, question first.
Why do you choose the guards for MLR?
Yeah, for now, we just want to formulate according to this. And it will be an exercise for you to really put a proof obligation for MLN. Yes, yeah. That'll be exercise. Okay, very good. So we got 5 concrete invariants. Let's do that. So it's going to be these guys over here. Okay, it's going to be A, a natural number, B, a natural number, and also C, a natural number. And also, I'm running out of space, but I'll just put it here. And also A equals 0 or C equals 0. Right? But it's orange, so you should really know that corresponding to these. Okay? Finally, we also need, don't forget, this typically is the most important one you cannot ignore. The concrete guard, which is over here. All right, finally, I'm going to put A plus B less than D, and then another one, C equals 0. You want to put them separately since they are more like a new lines, right, in the original form. So, yeah, you can think about these are the concrete guards of ML out. All right? So the whole thing actually about guard strengthening for ML out. Yes, question?
Isn't the fourth variant A plus B plus C equals N not A plus B plus C?
Absolutely. I agree. Thank you. Thank you so much. Good. All right, and exercise for you guys. And then we're going to do some proof. So exercise will be formulates guard strengthening proof obligation of MLN. Because this one here is for ML out, right? Let me see what's the name for that. Okay, if you go back to your slides, you will see that that's what we did. Oh, I see, okay. So the similar naming convention. So think about the whole sequence over here, right? I'm going to box it in purple. The whole thing over here, okay, the whole thing is called ML out, which is the events, and then we say GRD, guard strengthening, okay? So what I want you to do is to do MLN / GRD. You can definitely find the answer in the slides, but I would suggest try that yourself, okay? Many parts is gonna be same. These parts will also be the same. But for the concrete guard and the abstract guard for MLN, they'll be different. But you ought to know how to formulate that completely. Okay? Okay, good. All right, guys, any question? That's about formulation, right? So far we talked about the intuition behind why the guard should be strengthened. And number 2, what does it really mean when the predicate is actually stronger? Number 3, how we understand the proof obligation for guard strengthening and how we can derive the proof sequence. What's really missing is how do we prove this? That's the question. Okay? I would suggest we got about 20 minutes. I think we can do at least one proof completely. And then for the other one, I can maybe do halfway and then let you complete it. And then that'll be it for today. Okay? All right, so I think for your purpose as well, okay, why don't I leave this page clean just for you, okay? This is the first proof obligation. This is the one that we just formulated together, right? It's a guard strengthening for ML out, okay? I want to make a very quick notes for you. Okay, let me just see over here. So this part over here are the axioms. And over here, it will be the abstract invariance. Abstract invariance. And this part over here are the concrete invariance. Okay, concrete invariance. And these two are the concrete guards. Concrete guard of ML out. And finally, this is the abstract guard of ML out. Abstract guard of ML out. Right, that's again just for you to understand. And I can even tell you just for now, these are the only proof obligation rule you will need. Why don't you guys take maybe about 2 to 3 minutes to see how you may complete this proof using these rules only. And it may use some very simple arithmetic if you need to, right? Feel free to grab a piece of paper and write it down and then give a try. Okay? I think this is something you will need to know how to do next Thursday. All right? The only thing that may not be so convenient next Thursday is I wouldn't tell you which inference rule you can use. I will give you the PDF about all the inference rules. You can choose from there. But I wouldn't tell you the relevant ones. So you have to decide. Okay? I would suggest I'll give you 2 minutes. At least you can try anything you like. And then I will highlight certain predicates you may want to consider specifically. That might help you speed up a bit. And then we can do the proof together. Your mind should really somehow move very quickly about, oh, should I really grab this one? And then can it help me move a little bit forward, right? That's something you want to think about. All right, 1 more minute, and I'll give you 1 hint. Okay. Yeah, of course, any hypothesis you might decide to keep, they should really help you somehow eventually prove this one, right? Just don't forget the big picture. Okay, that's obvious. All right, guys, should I give you a hint if you don't mind? All right, 1 hint. Think about this one here, this one here, this one here. Okay, struggle with that a little bit more, and then I'll go over the proof with you. Okay? I claim that these are the only 3 hypotheses you will need. That should be enough to lead you all the way to proving it. So I'm just going to do one step here. Okay? By monotonicity, I can drop everything else. All I got would be A plus B plus C equals N. A plus B less than D, N less than D. All right. Of course, you may have different combination. You can feel free to try the proof and show it to me. I'll be more than happy to go over your proof with you. This is one possible way to do it. See, yes. Thank you, guys. Yeah, absolutely. Thank you. Yes. Yeah, thank you for telling me early. Okay, good. I'm going to make it smaller, and then I'll let you guys think about for 1 more minute, and then we'll do it together. Question?
So since we're dealing with just N and D, why don't we just keep the D greater than 0 and N less than or equal to D and then drop everything else?
Yeah, absolutely. I mean, that could be another path you can go for your proof. I would suggest also give it a try to see if that might lead you to, proving it. So what I'm showing here is just one possible way to do it. There could be more than one way, absolutely. Yeah. All right, guys, before I move on, okay, let's sketch a bit. My goal is really to prove this one here, right? I got some equality here. Why don't I, first of all, try to replace every occurrence of C just by 0? If I do that, it's going to be 0. So I got another equality, which means I can replace A plus B by N. Replace this by N, what do I have? N less than D, N less than D. Boom, I'm done. Hypothesis, all right? Looks easy, but it definitely takes time to plan that. All right, let's now do it. All right, so now I'm going to actually, first of all, circle. You can see this is the left, and this is the left. Sorry, this is the left, this is the right. Okay, I'm going to do EQLR. From left to right, which means I'm going to replace every occurrence of C by 0. That one is going to give to me A plus B plus 0 equals N, and A plus B less than D. That one doesn't change. And one thing here that's important, okay? I'll give you two choices. C equals 0 itself. If you only apply EQLR, that one cannot be dropped. But if you do believe that I don't need this anymore, what you have to do is you may want to say comma monotonicity again and then drop it. That one I will allow you to do in this step as long as you document it. But if you don't do it, it's actually considered strictly wrong. Okay, so I'll just do that for now. Say I don't drop it. Okay, and less than D. All right, so that one there is going to give me this. And let's say I don't need C equals 0 anymore, so I'm going to say monotonicity. That's going to give to me A plus B plus 0 equals N, and then A plus B less than D, and less than D. All right, so was it good? All right, we're almost there, okay? The only thing that's annoying, we can, well, if you only leave things like this, you can only replace N by A plus B plus 0. So you have to apply some arithmetic rule to say A plus B plus 0 is really just A plus B. I know it sounds very dumb, but you got to document the step too. All right, let's do that, okay? So you're going to say by arithmetic, I know that this part here is equivalent to A plus B equals N. And then I got A plus B less than D, and less than D, okay? We're getting very close. My goal is to really make sure I can replace this A plus B over here just by N, so that I got N less than D and N less than D, right? So now, in order for me to replace A plus B just by N, would it be from left to right or right to left? That's something you guys will have to decide, right? Either you want to replace every occurrence of the left-hand side, which is A plus B, by N. Seems to be what I want. But if you say RL, that will be replacing every occurrence of N over here by A plus B, which might be fine because you still got the same hypothesis, right? But the resulting sequence will be a little bit different. So make sure you know what you're writing. Okay? So I'm just going to do, let's say, EQ LR. So I'm going to replace A plus B over here just by N. And then I can also apply monotonicity at the same time to drop this one here at the same time. Okay? So that one there is going to give me N less than D. And also N less than D. Okay? I hope it's not too fast, right? It's okay? And then this one here, apparently it is really matching this and this, right? You got P here, itself is also hypothesis. And we're done. Okay, that's the proof. That's one possible proof. Question? Well, I see what you mean, but it's kind of up to you. You can either, yeah, I see what you mean. Even if you don't really drop this guy here, let's say you still got, let's say, A plus B equals N. This is more like an H over here. Yes, I agree. But it's kind of up to, you know, for me personally, I don't like to see, I just want to see exactly this and this. Yeah, but if you didn't really drop this one, it's still fine because you still got H over here. Yeah, I see your point. Yeah. All right. So guys, I think we got about 8 minutes. How about this? I wouldn't do the complete proof for the next one. That one is a little bit more complicated. Okay. How about I go over that one a little bit with you and then give you a little bit hints. You should really try. That'll be a very nice warm-up exercise for next Thursday. Okay. So the next one there turns out to be the solution to the exercise I asked you to do. Okay. Anyway, but I should really still do the exercise anyway. Okay. So this one here again. Here is, okay, let me just say, what you want to really notice is this is the abstract art of MLN. Okay, I'll show it to you. MLN, you can see the abstract art is n larger than 0, right? So that's why you can see in the consequence, okay? And then this part over here is the concrete guards. That's the concrete guard of MLN. All right? Everything else here would just correspond to the annotation I made earlier, these 3 parts. These 3 parts never change. You will just have to change the concrete guard and the abstract guard accordingly every time you talk about different events. Okay? Okay, what about you guys take about 2 minutes, all right? I might just let you guys go earlier today. I think I covered enough. So we can talk about invariant preservation on Thursday. So for this one here, why don't you guys spend 2 minutes? So these are what you need. 2 minutes, and then I'll give you some visual hints very quickly, and then we're done. Okay, just spend 2 minutes. Apparently, you can see this one here requires more rules, okay? Okay. And I'm even telling you, if you need this one here, right, if you actually got a disjunction appearing to the left of the turnstile, in that way, to really simplify it, you have to split it into 2 sequences over here, right?
Really? This wouldn't work.
Hmm?
This wouldn't work? That's surprising.
Well, you can try other ways. Maybe other ways will work too, but at least this is one possible way to do it, right? So I don't want to claim this is the only solution you should really follow, but you can definitely try to see if you can prove other ways. And show it to me, just in case you have made some mistake. Okay, 1 more minute. I'll give you some hints, and then I'll let you try. Okay. And the solution proof is also on the slides, so you can definitely compare your proof to my solution. Okay. Okay? All right, guys, ready for the hints? Okay. It turns out you need 4 different hypotheses. Okay? I'll circle them for now. This one here, and also these 3. 1, 2, 3, and 4. You need these 4. Okay? Give a try on this. It's not too bad, but somehow this will show to you how you can split, the sequence on the halfway through also into 2 independent branches, which we did last week, right? Give a try. If you really struggle with this proof over here, come by, and then we'll do it again together. All right, thank you so much. And then I think I will release the test guide about your written test number 2 by this coming Thursday's class. We can talk about it too. All right? Take care, and then I'll see you soon.